This is your presenter Asloob Mudassar, and I am presenting slide number 40 of the course on laser physics. Question is, calculate the absorption cross section under homogeneous broadening sigma h when an ensemble of NT atoms per unit volume is considered. Answer is, we have calculated the transition rate for a single atom in question 36. We shall now compute this quantity for an ensemble of NT atoms per unit volume assuming homogeneous broadening. In homogeneous broadening, the resonance frequency nu naught and the line shape are the same for every atom. Transition rate for the case of homogeneous broadening denoted by WH as a function of nu minus nu naught can be written as, so WH as a function of nu minus nu naught is equal to W as a function of nu minus nu naught, SA stands for single atom, is equal to 2 pi square over 3 n square epsilon naught into h square, and in the numerator we have rho multiplied by absolute square of mu multiplied by g of nu minus nu naught. This is in terms of the energy density rho, and the same expression in terms of the intensity I of the incident beam is given over here. That is equal to 2 pi square over 3n into epsilon naught into c into h square into capital I, which is the intensity of the incident beam, multiplied by the absolute square of mu into g of nu minus nu naught. So this is what I have written the transition rate for the case of homogeneous broadening in terms of the energy density and also in terms of the intensity of the incident beam. Photon flux, which we can define as capital F is equal to capital I, that is the intensity of the incident beam, divided by the h nu, that is the energy of a single photon in that beam. So F is equal to I over h nu. The absorption cross section sigma h is defined as sigma h is equal to WH over capital F. That is the transition rate divided by transition rate under homogeneous broadening divided by the photon flux, and that is in terms of the intensity of the beam is WH over I into h nu, as given in equation number 40.1. Using WH from the previous equation, we can write this equation as sigma h is equal to 2 pi square over 3n epsilon naught ch into absolute square of mu multiplied by mu multiplied by g of nu minus nu naught, as given in equation number 40.2. Change in photon flux through a thickness dz of the material containing NT atoms per unit volume with absorption cross section sigma h is given by. So we have written the change in flux df. When the beam of flux capital F passes through a material having thickness dz and that contains NT atoms, that is NT atoms per unit volume, and then multiplying it with the sigma h, we can get the change in photon flux. So df is equal to minus sigma h into NT into capital F into dz, as given in equation number 40.3. This equation can also be derived from equation given in question 10.1, which is given df over f is equal to sigma 2 1. Within the parentheses we have n2 minus g2 over g1 multiplied by n1, and outside the parentheses we have dz. Here g2 and g1 are the degeneracies of the level 2 and level 1 respectively, and the sigma 2 is the cross section of the transition from level 1 to level 2 to level 1. So using n2 is equal to 0, n1 is equal to nt, g2 is equal to g1 is equal to 1, and replacing sigma 2 1 by sigma h, we can have, let us derive another expression. So you see that we can use these values over here in this expression, and we can have the expression which is given above, that is in equation number 10.40.3, can be obtained from the expression using these parameters. So let's derive another expression for a df. You see that we have one expression of the df over here in equation number 40.3. Let's derive another expression for the df using another technique, using another approach. Let's derive another expression for a df, assuming that sigma a stands for an effective absorption cross section of an atom. That is, if n photons enter a sample of atoms, then n into sigma a photons will be absorbed. So now consider capital S as the cross-sectional area of thickness dz of a sample of atoms illuminated by an incident monochromatic beam. Then the number of atoms affected will be equal to n. That is, the total number that will be affected is represented by small n, and that is equal to nt into capital S into dz. You know that capital S multiplied by dz is actually the volume of the sample containing the atoms, and nt is the number per unit volume. So this, that is capital nt multiplied by S into dz, will then give you the total number of the atoms contained in that volume, which is denoted by small n. So n is equal to capital NT multiplied by S multiplied by dz, and the number of photons absorbed will be, you see that if you multiply small n with the sigma a, as we have explained over here, that is n multiplying by the sigma a will give you the some number of photons absorbed. So this is what we have done is over here we have the small value as n multiplied by sigma a, or equivalently the value of small value n, which is capital NT multiplied by S multiplied by dz and multiplied by sigma a. So this will give you the number of photons absorbed. This will appear as the change in photon flux df, where capital F is the photon flux of the incident beam. Thus, using this approach, we can write the change in flux df is equal to minus nt multiplied by S into dz and multiplied by sigma a, as given in equation number 40.4. So you see that we have sigma, we have delta F calculated from equation number 40.3, and also we have calculated through another approach given in equation number 40.4. Comparing these two delta F's, we get sigma H is equal to sigma A. That is the absorption cross section under homogeneous broadening for a sample of ND atoms per unit volume is equal to the effective absorption cross section of an atom. This is the end of slide number 40.